When you picture the San Francisco skyline, one building dominates the postcard, the Transamerica Pyramid. It's sleek. Sharp form seems to defy the very logic of building in one of the world's most active seismic zones. So, how do you build a 48-story pyramid that can survive a major earthquake? The answer lies not in a single magical material, but in a brilliant orchestration of different materials, each playing a specific structural role. This isn't a solid stone pyramid like in Giza. It's a sophisticated machine for living and working. Engineered with a deep understanding of dynamics and material science. In this video, we're dissecting the Transamerica Pyramid layer by layer. We'll explore the concrete, steel, and aluminum that make up its iconic form, and explain the engineering logic behind each choice. By then, you'll understand why this building is far more than just a pretty shape. It's a masterclass in resilient design. Let's start from the bottom, where the real engineering magic happens, the foundation. The pyramid sits on a foundation system designed to absorb and dissipate seismic energy. The building doesn't rest directly on the soil. It sits on a 14-foot thick concrete mat foundation. But the key detail is what's embedded within that concrete, a network of steel reinforcing bar, or rebar. This isn't your standard rebar, it's a dense, heavily engineered grid designed to hold the concrete together under immense tensile stress during an earthquake. Below this mat, 16-foot-long concrete piles were driven into the stable soil to anchor the entire structure. The combination of the rigid concrete mat and the flexible steel rebar creates a base that can move and flex as a unit without cracking catastrophically. A pro tip from geotechnical engineers is that the properties of the concrete itself were critical here. It had to have high compressive strength to support the vertical load, but also enough flexibility to work in tandem with the steel reinforcement. Now, let's look at the superstructure, the part we all see. The most common misconception is that the pyramid is a solid, load-bearing mass. It's not. The primary structural system is a reinforced concrete frame. The building's skeleton consists of 4 massive concrete columns at each corner, which taper as they rise, giving the building its iconic shape. These columns are connected by deep concrete beams and trusses at each floor level. The choice of concrete was strategic. Compared to a pure steel frame, a reinforced concrete structure offered more mass and inherent damping, which helps absorb vibrational energy from earthquakes and wind. But they didn't use ordinary concrete. The facade is made of precast concrete panels with a unique quartz aggregate. This was a deliberate aesthetic and practical choice. The crushed quartz is incredibly hard and reflective, giving the building its brilliant, sparkling white appearance in the California sun. More importantly, these precast panels are attached to the main structural frame, meaning they are part of the building's skin, not its primary bones. This separation between the structural frame and the cladding is crucial for allowing movement without causing damage to the exterior, while concrete forms the bones. Steel is the tendons and ligaments that hold it all together. Beyond the rebar inside the concrete, steel plays 2 other critical roles. First, some of the most critical structural elements, like the deep transfer trusses at various levels, are made of structural steel. These trusses help redistribute the immense loads from the tapering structure down to the foundation. Second, and most famously, the very top of the pyramid is crowned by a 212-foot-tall spire. This spire is not concrete. It's a framework of structural steel. Covering this steel spire are panels of aluminum, chosen for its lightweight and corrosion resistance. This combination of a strong steel frame and a lightweight aluminum skin minimize the dead load at the very top of the building, which is essential for stability. A common drafting mistake in less sophisticated designs is to use heavy materials at the top of a tall, slender building, which can exacerbate swaying. Finally, we have the internal elements that contribute to its resilience. The 2 wings that run up the sides of the pyramid from the 29th to the 45th floor are not just architectural flair. They are part of the structural system, housing elevator shafts and mechanical rooms. Acting as shear walls, they add significant stiffness to the structure, helping to resist lateral wind and seismic forces. Furthermore, at the very top, just below the spire, sits a tuned mass damper. This is a massive 30-ton concrete block suspended by cables. When the building begins to sway from wind or an earthquake, this damper swings in the opposite direction, acting like a counterweight to cancel out the motion. This use of advanced dynamic damping was groundbreaking for its time and is a key reason the building is so comfortable for its occupants during high winds. To summarize the key takeaways: 1. The pyramid is a reinforced concrete frame structure, not a solid mass. 2. Its sparkling white facade is made of precast quartz aggregate concrete panels. 3. Critical elements like transfer trusses and the iconic spire are made from structural steel, clad in lightweight aluminum. And 4. Its seismic resilience comes from a systems approach, a robust foundation, a tapering shape that reduces wind load, strategic shear walls, and a tuned mass damper. Now I want to hear from you in the comments below. What other iconic skyscrapers would you like us to deconstruct and analyze for their material choices and engineering secrets? Is it the Burj Khalifa, the Shanghai Tower, or something else? Your input guides our future content. If this look inside the Transamerica Pyramid was fascinating, please give this video a like and subscribe to Smithage for more content that uncovers the hidden science of famous structures.